All right, welcome to the lab. Today, we're diving into the absolute nuts and bolts of how we actually learn, going all the way back to the foundation of behavioral psychology. We're going to look at the groundbreaking theories of E.L. Thorndike. So, if you've ever wondered how practice, rewards, and honestly a whole lot of mistakes actually rewire our brains, you are in exactly the right place.
Let's kick things off with a real-life problem. Just picture a student struggling to open a really tricky mechanical container. Notice the steps she goes through here. First, she tries to force it using a bunch of unsuccessful methods, prying it, pulling it, twisting it. But then, after several totally varied attempts, she accidentally triggers the correct mechanism. Maybe it's a hidden latch. Now, watch what happens when she tries it again. She opens that container instantly. Her speed and execution have become significantly faster.
Which brings us to a pretty fascinating question. Did she suddenly understand the complex mechanics of that lock in this flash of brilliant insight? Or did that successful response simply become stronger through her physical trial-and-error experience? This is the exact puzzle that literally shifted the entire landscape of modern psychology.
To figure this out, we've got to look at the guy who basically solved this exact puzzle, Edward Thorndike. He was an American psychologist working right at the turn of the 20th century. Now, before Thorndike, psychology was largely about introspection. Basically, people just sitting around thinking subjectively about how they think. Thorndike changed the game entirely. He pushed psychology toward objective, measurable scientific observation. He started by studying animal behavior, specifically looking at how stimuli and responses interact. And then he applied those exact same principles directly to human learning and educational psychology.
And that brings us to his most famous experimental demonstration. Okay, so picture this setup. Step 1, Thorndike places a very hungry cat inside a locked wooden crate, which he called a puzzle box. Step 2, a bowl of food is placed just outside, right in plain view through the wooden slats. The food here is the stimulus. Step 3, the cat naturally exhibits all these random, frantic movements, scratching, biting the bars, reaching its paws out. But step 4 is where the magic happens. The cat accidentally triggers a hidden release lever inside the box, the door swings open, and boom, the cat escapes to get the food.
But here's where it gets super interesting. The actual data. Thorndike didn't just do this once. He put the cat back in the box again and again. On the very first trial, the escape time is a grueling 5 minutes of frantic thrashing. But on later trials, that escape time drops dramatically. To put that into perspective, it goes from 5 minutes down to just 5 seconds. The jagged, gradual downward slope of his data proves something absolutely crucial. The cat didn't have a sudden aha moment of human-like reasoning. If it had, the time would have just dropped to 0 immediately. Instead, what we're looking at is a gradual learning curve.
Thorndike coined a term for this that you've definitely used before: trial and error learning. This is a problem-solving method where you just make repeated, varied attempts until a successful solution is accidentally discovered. Over time, the useless behaviors, like scratching endlessly at the walls, fade away, while the successful behavior, pressing that lever, gets refined and repeated.
This brings us to the very heart of Thorndike's whole philosophy, known as connectionism or stimulus-response theory. According to this theory, learning is literally the physical process of forming and strengthening a mental bond between a stimulus, we call that S, and a response, R. In our experiment, the physical puzzle box is the stimulus, and the specific action of pressing the lever is the response. Learning at its core is just the strengthening of that specific SR bond.
From all those hours watching cats in boxes, Thorndike hammered out a theoretical framework that would end up shaping classrooms for a century. He called them his laws of learning. We've got the law of effect, readiness, exercise, and multiple responses. Let's break these down real quick because they are incredibly powerful.
First up, and honestly the most important, is the law of effect. The crucial takeaway here is this: responses that are followed by satisfying consequences are much more likely to be repeated. The positive outcome of finally reaching that food essentially stamped in the cat's escape behavior. On the other side, if a response leads to an unpleasant consequence, that bond gets weakened. Basically, our behaviors are entirely guided by their outcomes.
Next up is the law of readiness. You simply can't force an SR connection if the subject isn't prepared for it. Learners have to be physically and mentally ready. They need the right physical condition, the appropriate prerequisite knowledge, and above all else, motivation. Think back to the cat for a second. If Thorndike had put a completely full, sleepy cat into that puzzle box, it wouldn't have tried to escape at all. It would have just taken a nap. The cat had to be hungry. Motivation is an absolute prerequisite for learning. Then we have the law of exercise.
This is essentially the old saying, practice makes perfect. Well, actually scratch that. Practice makes perfect only with a massive caveat. Repeated practice does strengthen stimulus-response connections, but Thorndike later revised this law. He realized that mere repetition without a reward or feedback is actually completely useless. Think about it. If you practice a golf swing thousands of times blindfolded without ever knowing where the ball goes, you learn absolutely nothing. Repetition only works when it's paired with accurate feedback or some kind of satisfying consequence.
The fourth key principle is the law of multiple responses. When faced with a brand new problem, a single stimulus is going to provoke several initial responses. The learner will naturally cycle through all these different behaviors until the appropriate, successful response is finally found and strengthened. Again, this is the biting, the scratching, the wandering around the box that the cat did before finally stepping on the right lever.
So, let's pull this out of the lab and see how it builds in a real-life academic setting. Imagine our student practicing her multiplication tables. Initially, she's making errors. That represents those multiple responses. But as she gets the answers right and receives a good grade or praise from her teacher, there's your law of effect. And as she repeats the process over and over, that's the law of exercise, her correct responses eventually become totally efficient and automatic. Or consider another one we've all been through, learning to type on a keyboard. At first, it's frantic, right? The student is visually hunting and pecking for individual keys. But with repeated, rewarded practice, the reward being the correct word actually appearing on the screen, those specific finger movements form incredibly strong stimulus-response bonds. Eventually, the whole physical skill becomes completely automatic. You don't even think about it anymore.
And this totally applies to bigger, gross motor skills as well. Think of a child learning how to ride a bicycle. It is a chaotic system of pure trial and error. They wobble, they fall over, they overcorrect, but through repeated attempts, the brain establishes and strengthens the effective SR connections required for that complex physical coordination. The successful balancing movements get stamped right in. Now, once you've mastered that bicycle skill, how does it help you later on? Thorndike explained this with his theory of identical elements, dealing with the transfer of training. The idea is that earlier learning only aids a new task if the second task shares identical elements with the first one. Because you've already established strong SR bonds for balancing on a bicycle, that training transfers almost seamlessly to learning how to ride a moped because the physical environments and the balancing elements are nearly identical.
Now, as groundbreaking as this was, we do have to look at it critically, because Thorndike's approach definitely isn't perfect. When we compare his very mechanistic trial and error approach against complex human reasoning, a pretty big gap emerges. Critics rightly point out that Thorndike's connectionism paints the learner as this passive machine, just blindly reacting to stimuli. It doesn't really account for complex human reasoning, deep understanding, or active knowledge construction. After all, humans aren't just cats in boxes. We use language, abstract thought, and sudden moments of real insight to solve our problems.
But even with those limitations, Thorndike's enduring legacy is just monumental. I mean, he essentially established the entire field of educational psychology. He taught us to break complex tasks down into bite-sized, manageable parts. He popularized using praise and rewards in the classroom rather than harsh punishments, and maybe most importantly, his law of effect laid the exact foundation for the next massive leap in behavioral psychology, operant conditioning.
Which brings us to a pretty compelling final thought. Thorndike proved that the outcome of a behavior dictates whether it's going to happen again. So, I leave you with this question. If consequences can strengthen a behavior, what happens when a behavior is precisely followed by systematic reinforcement?
We are going to answer exactly that in the next part of our Explainer series. Thank you so much for joining me in the lab today. Be sure to check out our next explainer on Pavlov and classical conditioning, where we're going to see how these mental associations go even deeper, right down into our reflexes. I will see you there.